Good morning, everyone. Thank you to the organizing committee, Hosho, Saki, and Masakito for the kind invitation. I'm very excited to spend a week here on this beautiful campus talking about non-equilibrium dynamics with all of you. As you said, my name is Derek Wang. I'm a research scientist at IBM Quantum, and I'm excited to tell you about our work that we call a detailed portrait of quantum many-body dynamics. And I'd be remiss in not thanking the authors on this course. Let's let up the theory here. Mung and Nikhil were interns at the time. Was come back as a full-time student. Nikhil's now a student with Adam Kaufman. Ali Reza and Ramis also did theory. Ramis is at Google now. And then Zlatko was our senior PI for this particular project. Okay. So the broad motivation of not just this work, but pretty much all the work that us as a research team do is can quantum computers be useful for many-body physics in the next 3 to 5 years? And since it's a bit early right now, and I want to get everyone kind of interacting and excited about it, I'm going to do a little poll. The last few options: who thinks the answer is yes? Who thinks the answer is no? Who doesn't know enough to say? And who wouldn't answer no matter what question I look? Okay, so the first one: who thinks the answer is yes? They will be useful in the next 3 to 5 years. 1, 2, 3, 4, 5, 6, 7. Okay, 10 or so maybe. And who thinks the answer is no? Okay.
I would say 10 years.
10 years, okay. 10 years, a little longer time horizon. Okay, so maybe 15 or 20 people. And who doesn't know enough right now to have an opinion? Okay, yeah, maybe a little fewer than the people who think that the answer is yes. Okay, so by the end of my talk, I hope to convince you that if the answer is not at least yes, that they will be useful, that perhaps they can at least be interesting. Yeah, so let's see if we can get to that point. So when we talk about doing quantum dynamics in particular on quantum devices, and we describe ours as a large-scale superconducting quantum computer, we typically parameterize these problems in terms of what we could run on it in terms of quantum circuit. So a quantum circuit looks like this. We have time going from left to right. We have qubits here, so this is 1, 2, 3, 4 qubits. And then we can run gates that are logical operations. These are Rx gates. These are 2 qubit C0 gates here. And we typically think about how many 2-qubit gates we can do. And since we can do them in parallel, we might think about how many layers there are. So here there's 1, 2, 3, 4 layers. It turns out the 2-qubit gates have errors about an order of magnitude larger than the single-qubit ones on hardware, so we just keep track of the 2-qubit ones. And so what we can do is we can make this plot of the number of 2-qubit gate layers, call that depth, and the scale, the number of qubits. And clearly, anything in this green regime is pretty easy to do. Basically, for, let's say, 1 qubit for any depth, we can evolve forever in time on a classical computer. And then even if we had 100 or 1,000 qubits, we could evolve a couple layers into 2-qubit depth for sure as well. And so our goal in this line of research is to always push out to this top right corner here to get harder and harder quantum circuits, at least by this naive metric here. And in the past few years, we've been doing that with various research studies that have come out from the device, not only by internal researchers, but external ones as well. And so I plotted some here, some of these studies in terms of what's on this plot. And so in the context of the whole field of quantum computing, this is where today's talk is going to be. It was at the time one of the largest quantum simulations. And so hopefully we can learn something from it. So now going back to the actual study that I'm talking about today, the motivation is broadly to think about uncovering the dynamics of many-body systems. I don't think I need to motivate much for this particular crowd here, but we know that quantum many-body systems and their dynamics, they're very interesting to learn about from a fundamental science perspective, and perhaps even useful technologically. But generically, they're very difficult to understand and simulate. We can make progress, though, using symmetries, conservation laws, and integrability. This is the theme of the entire workshop, I believe. And with this, we can unravel intricacies about these complex systems, but they can be difficult to discover. However, once you discover these laws, these conserved numbers, you can make great progress in understanding what's going on. And so we can do this, we can understand this with the simplest example from harking back to high school level classical physics, right? You might have this question posed to you, 2 billiard balls are coming towards each other, there's an elastic collision, there's some speed before, and we want to know the speed afterwards. How do you solve this? In high school, you kind of learn to write down a couple of equations. You write down the equation for the total linear momentum, you write an equation for the total kinetic energy, and from there you just kind of do some algebra and solve, and you get the right answer. So we've been doing this since our high school level classes. And in some sense, then, you can find enough integrals of motion for the system that you can fully learn the dynamics. This is the theme of the work. So in quantum physics, we have something quite analogous. We have these integrals of motion, but rather than being these single numbers, they are represented by operators L. And so if we have some system, quantum system here, evolving over time with unitary U, then this integral motion L should commute with the evolution, with the Hamiltonian as well. And therefore, the expectation value of this operator should be constant over time. We can also then just write this out generically as a sum or some basis. In this case, we'll choose the Pauli basis. It's very convenient when working with quantum computers. And there's generically 4 to the n of them. So then generically speaking, it is not easy to write down these integrals of motion. So unless you have a particular trick, you can't simplify your system this way. Discovering them can also be difficult, but not always. We can consider this very simple system here, this Ising model here with z potentials on each site and zz's between neighboring sites, let's say. And you can just kind of stare at this and figure out exactly what operators are going to be conserved. The z0 will be conserved, that commutes with the Hamiltonian. Same with the z1 and the rest of the qubits. You can run, I think, like 2 at the end of these. From here, you can write down these integrals of motion. There's an extensive set of them. You can label the eigenstates, and all of a sudden, this trivial toy model becomes quite easy to simulate and understand through this lens. But generically, this is our problem. So what is one way we can simplify quantum dynamics when we don't have something we can just stare at? This. In some cases, we might be lucky and we'll have local integrals of motion. Local integrals of motion, you have the Paulis not summed over all 4 to the n of them anymore. They're going to be over some local neighborhood. K, where K is the center qubit, let's say, and then K plus 1, 2 is the neighboring ones there as well. And then if you can find many hidden local integrals of motion at the same time across the system, you can say something about integrability and something about dynamics. And so while this is perhaps not the most precise description for this crowd, generally we can say that if a system is described by an extensive set of local integrals of motion, is quantum integrable. We'll go with this definition moving forward in today's talk. So what kind of systems will you find this kind of these local integrals of motion? One is in this regime of many-body localization. In many-body localization, you have random disorder across every particle, and there's also hopping or interactions between these sites. And so if the competition between the hopping and disorder is right, you have high enough disorder, then you should be able to see that you can go from this ergodic regime to this more localizing regime, where the dynamics are more localized. And so the hypothesis is that above this critical disorder here, these systems are suspected to have an extensive set of local integrals of motion. Yes?
Yeah, so I have a question regarding the previous slide.
Yeah.
So if I'm not mistaken, I mean, of course, I know the authors of that paper. The local integrals of motion there means maybe integrals of motion with local densities. But here for MBL, the local really means local. I mean, it's literally localized. So I wonder if you distinguish these two. Because, for example, the Hamiltonian is an integrals of motion with local density instead of being local.
Yeah.
You see what I mean?
Well, I guess I'm not quite sure.
Yeah, for example,
in this case,
the spin chains that we consider to be quantum integrable, they actually do not have much local integrals of motion, but they have integrals of motion with local density.
Mm-hmm.
Yeah,
such
as all the higher charges. That's what transformations is. So.
In this particular case, we'll be thinking about geometric locality the entire time, just based on the way the device is connected to each other. It'll be in this fashion. I guess
so it's really local.
It's
really local.
Yeah, like physically local.
Okay.
I can't comment on it.
Yeah. Okay. Thanks. Yeah.
Great. Thank you. Okay. So going back to this, yes, Boston critical disorder, we have these localizing dynamics. And so the hypothesis is that in MBL, the original Hamiltonian can be written as a sum over these local integrals of motion, where these coefficients, J, get smaller and smaller as you increase the number of terms in that particular interaction. So as an aside, if you're new to local integrals of motion and many-body localization, probably not so much for this crowd. Last year, there was this nice Boulder School for Dense Matter and Materials Physics. I think some of the people here are also there. And Zlatko gave a talk on this work there. There might be a recording. There's also these reviews that are really nice. And just a quick little plug for one of our own outreach experts is this IBM Quantum seminar. We host this every Friday on YouTube at 12 p.m. Eastern, and we host professors and students to talk about their latest research. We had David Hughes about a year ago talk about MBL. And if you happen to be interested in giving a talk of your own there, just email me and let me know. Yeah.
If you didn't want to talk about disorder,
Yeah.
I mean, is the implication that the typical perturbation of a if you didn't want to talk about disorder, is the implication that the typical perturbation of an integrable system, the integrability is irrelevant when you have a large number of particles?
So can you say that again?
Could you go to the previous slide?
Yeah.
Yes. So when the system is coupled,
Mm-hmm.
or the disorder strength is low.
9 in this case, yes.
Yeah. I'm sorry. The disorder strength is high.
Yeah, disorder strength is high, yes.
I understand. So it's integrable for different reasons. I mean,
Yeah.
it's all for different reasons. Thank you.
Okay. Yeah, sorry, that was the question. Okay. Any other questions? So then, okay, so we have this quantum seminars. You should email me if you'd like to speak on there. And there's also a lot of experiments related to many-body localization in the past few years that explore different systems on different types of quantum simulators, looking at properties of different complexities. And Pedro is here in the audience, you can see they've also done great work on many-body localization. So we're not the only ones out here, but I hope to convince you that we are doing something that is differentiated from the rest of the work you see here. So the specific question that we're answering then is, can we uncover all integrals of motion of a large disordered many-body quantum system using a quantum computer? And to give you a preview of the results and what the study looks like, the most complex system that we look at is doing quantum simulation of this 2D interacting many-body flow case systems on 124 qubits. We have this system here where it's kind of artificial, where we imagine that they're connected in this heavy hexagonal lattice. Heavy hexagonal means there's a hexagonal connectivity, but you have extra spins on every edge. So every loop has 12 qubits in it. And we choose this because it happens to map exactly to our device. If you have questions about why the device happens to look like this, I can explain that at a later point. And so what we're showing here is just the learned noise map of the entire device. So we're mapping one-to-one spin to qubit. The experimental setting is 124 qubits. We go to a depth of 60 and 2 qubit layers. This corresponds to a flow case depth of 20. This is because it takes 3 layers of Sinan gates to do every set of unique interactions between every qubit. And in this particular paper, we submit over 1 million circuits to the device, 1 billion shots. This takes about 80 hours to run, just to give you a sense for the scale of the study. And I think something that's quite interesting is that it's all done through the cloud. For those who are familiar with the quantum computing world, you might already know this, but we can do all these experiments just through a laptop on Jupyter Notebook. We can have you logged in and running it in just a few minutes probably. And so I personally have never even seen any of the devices that I run on. Okay. So this is what the device looks like. These are these 3 different colors I was telling you about, where you have 3 layers to do each flow case step to get every connectivity there. And since it's a fully controllable device, we can do things like initialize specific sites in specific states. So here we'll initialize these to the 1 state. This spells out the IBM. You might have seen that in the very first slide of my presentation here. And it's just kind of a little reference to how IBM and Zurich, they spelled out IBM with single atoms some years ago in Zurich. So we're doing the same thing on a quantum device today. And from there, we can do flow K evolution and control these parameters theta and phi. And what you see is that now the dynamics will take on two very different kinds of character. Going from steps 0 to 10, you can see that pre-thermal regime, this IBM thing, looks like it's conserved a little bit better than in this case here, where almost immediately you see the information just get dissipated in this single set basis here. So in the study, I said like MBL experiments are characterized not only by the system, the device you're doing it on, but what you're measuring out. In these kinds of studies, it's very common to measure something called spin imbalance. In the spin imbalance, you're basically measure out single Z operators on every single qubit, and the spin imbalance is just like an averaging over some set of them. And so we like to think of this as like very, very coarse image of the dynamics. You can do like a qualitative probe. You can generally see if it's localizing or thermalizing or something, but you can't really see the full details about the system just from this very coarse probe. So then we introduced something that we think we've done for the first time, which is measuring out these one particle density matrices. These can tell us a little bit more and tell us more precisely whether we're observing some kind of finite phase transition between the thermalizing and localizing regimes. And you can start to see what we're actually trying to spell out now here. It's still coarse, you still can't quite see everything. And then, our hope is that we can uncover all of these local integrals of motion here and uncover effectively what is the original image of this system, the Mona Lisa. Okay. So now let me dive into the system and experiment here. Yes?
One small question. So when you say local one particle density matrix, exactly what do you measure here?
This is the expectation of AI AJ minus expectation AI times expectation AJ.
Oh.
Yeah. So let me talk about the system experiment now. So the system is some spin lattice system over potential. There's a disorder potential underneath. Every site is going to have some randomly sampled one. And then from there, like I said, we can do this unitary Fouquet evolution, and then we can measure out any basis we want here. This unitary Fouquet evolution looks like this here. And so we have this kinetic and interaction term here in blue. So it's this CZ gate here, this controlled Z gate, and the interaction is controlled by this angle theta. And then we have spatial disorder. And the spatial disorder is randomly sampled for every qubit differently, but notably they're the same from step to step. Otherwise, that would just look like some kind of decoherent noise. And you can see that what the formal definitions of the gates are over here. So then from this, we can extract information about the dynamics of the operators, whether localizing or ergodic, for example. And then we can use this information extracted from every step of these different polys to then reconstruct the local integrals of motion. This is kind of a technical step here, and so if you are not an expert in quantum computing or not interested, you can feel free to zone out for a second. What we do here is to extract results that are of higher quality from the device. You use a technique called error mitigation. The devices on their own are quite noisy, and to go out to a depth of 60 with 2600 some 2-qubit gates, you would basically get nothing. And so we don't just run the circuit there. And my job for this particular project was actually optimizing this process here. And what we can do is we can submit these circuits to what we call an error mitigation factory. And then these circuits will undergo various transformations. They'll be executed on the device together, and the results can be recombined to give results of higher quality. And I just want to give you very briefly a kind of quick run through of what this might look like and how that these calculations on the device are really closer to experiments in a way. We're really thinking about signal and like post-processing steps and trying to get the most out of the device. So the first step is to use something called zero noise extrapolation. And the basic idea here is this. If the noise is of a particular form on the device, as you increase the noise, you should see a functional dependence of the expectation value of the circuit with the amount of the noise. Then the question is, how can you control the noise very precisely? One way to do this is to increase the number of gates in the circuit, but don't change the logical meaning of it. So what we can do is here, this blue gate here, we can add 2 extra gates. These 2 extra gates will be U and U inverse. So overall, they equal the identity. We're doing the exact same thing, but now we have 3 times more gates. So the idea is to have run this circuit and this circuit, and then we get the expectation values of these 2 different noise values, and then we can extrapolate back to the zero noise value and hopefully get a better result. Something else we can do is called twirling or randomized compiling. In this particular technique, what you do is you append random poly gates before and after these 2-qubit gates. The overall effect of this is to reshape the noise in a way that you take coherent noise and change it to incoherent noise. And then from this point, the noise stacks up way less quickly. So your signal is stronger for a longer amount of time. And it's also obeys these assumptions a little bit better that we have in zero noise extrapolation. The next step requires some understanding of our particular device's physics. So on the IBM devices, the qubits are created in such a way that they have this always on ZZ interaction between every qubit all the time. This is obviously a problem when you don't want to do, as Ed said, time evolution. And what you can do is you can use dynamical decoupling pulses to effectively cancel that evolution out. And so this is where we have to talk with people who actually build the device, understand the parameters, and can design these kinds of injection of gates. Once we pass them through this factory, we have a lot of circuits that are coming out. This is how we get to something like 1 million circuits, I said before. We pass them to the device. From the device, we get this counts dictionary, and we just basically get every measurement and how many times they appear. 0, 0, 0, 0, happen 20 times. And then we do a lot of post-processing. We can correct the readout by doing calibration. We average over these randomly compiled circuits. We extract competing values, so we try to get as much information as possible. We do this digital zero-noise extrapolation. And finally, at the very end, we get a result that looks like the expectation value of some operators over time. Yeah.
What do you overhead for error mitigation?
Yeah. This is a very highly debated question. I think it really depends on the situation. Generically speaking, the overhead is exponential, right? So with the amount of noise, the number of circuits you need to run to extract the signal is exponential. But there's also work coming out that shows, like, depending on the circuit class, you find that the noise spreads a little less quickly. And so in this case, we do a circuit overhead of just 10. So we put in one circuit, we get 10 circuits out because the noise is so strong that we need to do this like many large number. Yeah.
So I want to know, when you do error mitigation, what do you compare to? So you got some result from the machine. So how do you know the error is minimized or not? What is the standard you're comparing to? Is it some theoretical prediction or?
Yeah, the typical thing we do is we try to look at the results for small systems for very large depth, and large systems in the Clifford limit where we can simulate them exactly. And then from that point, we hope to have enough confidence that we can start to extrapolate in between. And since the development of like these kinds of benchmarks, there's more things they can do to make sure that from a hardware perspective, crazy things aren't happening. Like the noise isn't suddenly changing in the middle of your execution of circuits, and some static monitoring jobs in between as well, just to check the health of the device. So that's kind of the battery of things we do nowadays to make sure that the results are trustworthy.
Okay.
More questions? So with all these preliminaries, finally we can start to jump into the actual results that we got from the hardware. First, we'll do some benchmarks. We do this for both 1D systems and 2D, 1D for 104 qubits, 2D for 124 qubits. And so in the paper that you can find online, we do all of these things where we do spin imbalance. This is the coarses experiment I mentioned before. We do these one particle density matrices experiments as well. I won't talk about this today, but I can afterwards for sure. And we also do classical numerics just to make sure that there is a proper finite size phase transition. And I also won't talk about that today, just the spin imbalance for now. And then from there, we'll go on to the Liam's results. So this benchmark here, what we can do is take this system, which is going to be now 104 qubits, snaking across the entire device here, like this. And then what we can do is initialize it in this anti-paradigmatic state and run one of these very classic spin imbalance experiments. And so then we know from our numerics that if theta, the coupling, is below some value that we found, it should be more of this localizing behavior, and it's above that we should see this thermalizing regime. And so these are results that we actually get from the device now. See, this is theta 0.1 pi, this is in that localizing one, and this is in that thermalizing regime. And we've done is we're just showing results from a cut of 12 qubits in the middle of the chain here. And so we initialize in this 1, 0, 1, 0, 1, 0 state, and we're evolving over 20 full case cycles in this case. And you can see that in this more localizing one, we get this nice conservation of the original spin pattern, whereas in the thermalizing case, they disappear almost immediately. And then from this, what we can apply is a spin imbalance. This is basically the difference of the populations on the 1 and 0 sites. So if this pattern stayed here perfectly, you would expect that this value to stay at 1. And if it dissipates, you expect it to go to 0 very quickly. So what we call our MBL regime here is you can see that it decays. And if you strain your eyes really hard, you can see that it plateaus at this particular value. We don't find that particularly convincing ourselves, though. So we have done, just in the last week or so, redos of this on a better device with more advanced error mitigation techniques. And we can properly see this plateau here, but I couldn't get it in this presentation fast enough. And then the second one is the ergodic regime at 0.3 pi. And you see here that we get this fast decay. It looks like there's two slopes here going on. There's this faster one and this slower one. We think this maybe has to do with more of the noise of the device, and this could be more of the intrinsic dynamics that are going on. This is something we haven't quite resolved yet either. Then we can do the same thing in 2D. So in 2D here, this is a GIF of going for 20 steps. In the pre-thermal regime, you see the pattern stays alive a lot longer. This one dies. And then you can see a very similar pattern here in the spin and balance over there. And we also do more. Yes.
So I may miss your explanation that you're in the record about such a randomness. Are you taking some other rate of randomness or some or you are showing the single random simple profiles?
Yeah. So this one here is over. This is over just one instantiation of randomness over the 100 and some qubits there. And so if your question is, do we calculate the spin and balance over multiple instantiations?
Yeah. Sometimes in the dynamics and there we in numerics in like classical separation we do the taking average to get the more sharper.
Yeah. No, I think each of these is just one instantiation, but because this is like over 100 qubits, the shape of the curve doesn't change very much. And we've done this like in simulation as well. Like, of course, each of these individual curves is going to change for every qubit. But once you do the averaging, it just averages out.
And also, one more question is that you show that the more recently they use actually see the plateau in the MPL regime, but in theoretically it is a finite system. So if you wait for sufficiently extremely long time, in theoretically need to be summarized, right? So
yeah. I think that's just a general issue with this entire type of work, right? We can't simulate out to the times that you can on a classical device at all.
But you didn't see some such a pre-thermal behavior, right? Usually the plateau, but if you wait for a longer time, that will summarize again. So.
Yeah, we could try to go out deeper. I think that there would be, first, just details with software would be really hard to do, but secondly, the noise would be just uncontrollable at that point, and we wouldn't be able to resolve any of these effects anymore, most likely. Yeah, and so what we do is we just, a lot of these results we show up to the point where we're just quite confident that the signal is still reasonably there, something like 10% or 5% of the original signal. We feel confident, okay, we can recover that with error mitigation. But beyond that, we start to lose it in things like shot noise and just extrapolation errors.
I see.
Yeah. Any other question? So then we do some more benchmarks as well. These are experiments of the one particle density matrix where we can observe these kinds of like inversions here to say that, okay, we have some sort of finite size MBL, at least within the 6 to 10 qubit range. And we also do these classical numerics where we look at gap openings. I won't talk about these further, but I can talk about them afterwards just because of time constraints. So let's finally now jump into the local integrals of motion, the highlight of this, I hope. And the concept of extracting local integrals of motion is actually quite intuitive, although it can get kind of thorny in practice. The concept is this: consider your spin chain. And at this point, there should be some clear understanding of how we extract the expectation value over time or the number of full case steps. And so we can do this for Z4. We can also plot the curves for other operators in this local neighborhood. And then we can measure many of them. And then from this, what you do is you basically try to find a linear sum of them that over this time period that you've observed, that summation of these operators is constant. And so in this case, it just so happens perhaps that these four give you this nice controlled operator that equals a constant, and that would be your local integral motion. And so your idea is to identify these polys in this local neighborhood and then find these coefficients here. And because you can't just do this for one particular initial state, it might be different for different initial states, you also are going to repeat for ones. And so we repeat over initial states combinations in the Z basis, X basis, Y basis, and combinations thereof. So from the device, we can do this error mitigation, get these expectation values for many, many operators in that neighborhood. These are all of the operators that we're considering in our optimization for qubit 50 in the middle of this chain, or 51 or something like that. And of course, it's quite chaotic. It's really hard to see what's going on here. but with some of this post-processing, we can extract these local integrals of motion. This is the best that we can do for this qubit here in L50. We can compare this against what we would get from an ideal case, where we simulate the evolution over 12 qubits, 6 before and 6 after in this system. And we can see that, of course, in the ideal case, it's a lot more stable, but this is an experiment after all, so we get a little bit of noise here. And so this local integral motion here is now, we have all this information. We can write it as a sum over polys in a local neighborhood, and we know these coefficients. And from there, we can start to explore the structure of these local integrals of motion. And what you can do is you can look at the different weights of the polys inside of it. Maybe it's intuitive that it's largely of this single Z character, right in the center of this neighborhood. There's a little bit of X. I think this probably comes from the theta interaction. And then these are less intuitive. These are things that you probably just would not have written down on your own if you try to come up with an ansatz for it. They are low weight. They have largely Z character, but the order, the numbers, they're kind of hard to understand. They just come out of the numerics here. So that's one local integral motion for qubit 50. But the idea was to find all of them. So how can we do that? Well, first, let me show you that we can plot the density over all the poly weights as a function of the weight of the poly 0, 1, 2, or 3 in that neighborhood. And this is the one we got before. It peaks right at the center, and then maybe there's this exponential decay over here. And the thing is that we can extract all of them from the device simultaneously. Remember, we're doing measurements in a local neighborhood, and we can do measurements across the entire device simultaneously. So we can measure all the information we need to get the information for these Leos simultaneously. Therefore, this procedure does not really scale with system size on the device, again, because everything is local. So what I'm showing here is just every fourth Leo, 0, 4, or 0, 3, 7, etc. Counted right there. And then this is like the alternating ones, and this is the shapes of all 104 from the exact same experiment. They all largely have the same kind of shape, this exponential decay there. And so going back to what I said at the very beginning, the idea was to extract local integrals of motion, an extensive number of them. And this is the very first evidence that we can at least try to get this kind of information from the device. I'll talk a little bit more about what it says about the ultimate integrability of the system and like the error in just a couple of slides.
Question.
Yes.
If you solve this, is this meant to work? Did you solve here like simultaneously? Are we looking at the same local observable and it just shifted? I mean, maybe a question was a little about the slide before where you identify one, then you said you also simulated. So
I see what you mean. Okay. So we extract this data from the device. It's basically a long list of polys that are centered at different qubits. And then from different segments of the data set, for all the polys centered around qubit n, we get Leo n. And then from the other part of the data,
that's it. How do you get Leo n? How do you know what operator to choose and what is the prefactor?
Yes. Okay. So yeah, once you have this database of the poly operators around n, which we can we measure basically out some local neighborhood of like 3 on every side or something, and then from there, there's a few different methods for getting out this the coefficients. One is where you just solve the optimization problem. So you just say that I want to set the constraint that the coefficients squared must add up to 1, and I want to minimize the error in how they change over time, and you just solve this optimization problem. The problem with this is that it's quite unstable, this solution, and there's this risk of overfitting as well. And so then we actually use this result as an initial guess in another procedure that we just got from literature from like 10 years ago or something, where you basically compute the average inverse time evolution of some initial guess, and then you measure out the projection on every individual poly operator you want to project it on. This particular procedure is highly sensitive to the initial state you put in. So this is why we initially solve this optimization problem to get a guess, and then we put it into this next procedure to get something that's a little more stable and convergent, and then this is the final result. Yeah. I think I have a slide somewhere about this, maybe not in this main presentation. Yeah, questions? So at this point, I think we should take some caution. I think this was talked about by various members here is, can you really make a statement about the ultimate integrability of the system? No, I don't think so. The uncovered Leoms are conserved over this observation timescale. They're minimized to the best that we can see. But then considering this long time limit, they're always going to be understood as approximate. Deciding this ultimate integrability of the system is challenging. But the hope is that this procedure here is just at least a blueprint of how we would get this information from the device, and as the devices improve, we can get better and better descriptions on these dynamics. Okay, so then from here, we can also start looking at the weights over in like different poly weights. So here, this is showing the density over weights of poly 1 over here. This is the density over polys with weight 2, like a ZZ, 3, and 4. And then we can plot them here, where we look at the position and the operator weight here, compare the theory versus experiment, and we can see we get pretty decent agreement across several orders of magnitude from 10 to the 0 to 10 to the minus 2 or so. But then we can see where we faded out, probably not such a fair description. We start to fail a little bit out here as we increase from the, go farther out from the center qubit. And we do generally less well as the orders of magnitude of these weights goes down. So why is this the case? Well, when the operator weights go down and we have coefficients of order 10e minus 2, at this point you start to see the effects of like shot noise on the device. Remember, this is a quantum computer, sampling from it. Your shot noise scales to something like 1 over the root of the number of shots you're taking. We take something like 10,000 shots. It's really hard to resolve like any observable more than like 10e minus 2. We can of course increase the number of shots, but then the experiment gets really expensive. And then why are we doing poorly as we increase the neighborhoods out here? Well, precisely in this experiment, these are details I haven't talked about. We look at every poly within this neighborhood of +2, -2. So every X, Y, Z, I combination you can imagine. But then once we go out here, we don't do that, and we just have like high weight polys that commute with the ones closer to the center. So we just don't have so much precise information out there. So you can see this kind of systematic error as we go farther out from the center of every Leom. You might also be wondering, how good quality are these Leoms actually compared to what you might try to get out of a classical simulation or something? And so how can we try to estimate that? Well, if we say that the guess for Leom is going to be, let's say, the single Z operators, just like in that first Ising chain case, that toy model I showed earlier, what you can do is you can compute the error from like how conserved it is by looking at the commutation of the flow K operator with that guess. And it turns out when you do this guess for the local integrals motion, you get this error of about 0.23 in this bottom corner. So that's the reference to be. We want to be 0.23. Can we do that? So then what we can do is we can plug in all the Leoms that we get from the device, compute this commutator here and normalize it, and then we can look at the errors of all of them across the device. And you see something for like 80% of them, we get errors below 0.05. And then maybe 15%, we get errors a little bit higher, but still below this metric here. And then for some of them, we actually get quite bad errors. Greater than 0.04, I would say some of these are actually above this 0.23. So what we get from the device is worse than if we had guessed classically in the first place. And so why is this the case? This is where the kind of experimental intricacies come into play. You can see these Leoms all seem to be clustered around specific qubits here and here. And so this is suggesting to us that the device might have just been not performing well in that particular day. The gates aren't doing so good, but the readout's not very good there either. So the upshot that we sell about this is sometimes, well, we can use Leoms as a way to probe the quality of the device. And there actually are works doing this exact same thing where they try to simulate MBL systems on devices, and they can kind of estimate the quality of the device based on the quality of the results that you come back. Now we get to skip to the 2D case here, and we do the exact same thing to get all 124 pre-thermal Leoms. They are, in this case, definitely pre-thermal and approximate. And this GIF is just flashing through the densities of every single one of them, 25, 26, 27, as we go forth. In this case, there are actually 2 different kinds of Leoms depending on their geometry. There's the 2 vertex ones, the 3 vertex ones. And just like in the 1D case, we can break them apart by weight of the poly, 1, 2, 3, and 4. I would say what's interesting here is that the weight 3 ones are actually higher weight than the weight 2 in this case. And this is for a reason we honestly don't really understand yet. But I just wanted to point that out to you in case you also noticed this. So coming towards the end here now, what we've done is that we can now get very operational Liouville description on these observational time scales. We can break apart the Liouville in terms of their weights. We can see all the individual coefficients for every individual one. And we hope that this is something quite close to the fully pixelated version, non-pixelated version of the Mona Lisa here by analogy. And so what can we do with these Liouville in the future? We can look at the site-based localization lengths, for example, as a probe for how localizing or thermalizing that system is. Maybe in the future, we can look at melting of these Liouville across phase transitions. We wanted to run this experiment, but ran out of device time for recovering and tracking local scalable information. So I think a cool experiment would be to initialize in some state, evolve as many-body Hamiltonian, the Spokane Hamiltonian, get the results out, and then evolve back classically to see exactly what the original results were. And this could be a nice, fun way to demonstrate like a quantum memory inside of like a NBL system. So in summary, we have this many-body dynamics with 124 qubits, depth 60. We've restored this portrait of systems localized through thermodynamics. And looking towards the future, we hope to use the system as a playground for competition, quantum versus classical, make the systems powerful enough that we can look at localization lengths that are large enough that you cannot study them classically anymore. We are thinking of using Liouville for proper calibration of the hardware. We had hoped to add to the discourse about the fate of NBL in 2D, but in this case here, we couldn't actually see a finite size phase transition on the device. And then we're also thinking about studying other initial states, thermal states, some topological NBLs, something that we're thinking about now, and various other phase transitions. And going back to the original theme of the motivation of this work, it's not just a many-body experiments. It's also, I think, a statement about where we hope quantum computers to be in the far future. And so this is just one of the many works that we're doing on large-scale quantum computations. And I know this particular workshop is about dynamics, but if you're interested in these other things, I'm happy to talk about them. For example, we've done long-range entanglement using dynamic circuits or circuits with mid-circuit measurements and then feed forward that information and teleported gates across 100 qubits. We're exploring the intersection of machine learning and quantum computing. In this case, we're using for error mitigation. So that whole error mitigation factory I showed earlier, we're trying to wrap that up into a machine learning model and to basically train on all the circuits that we ever sent to the device and minimize the overhead for doing that on an experiment by experiment basis. We're also thinking about learning quantum noise at scale. This is really important for understanding devices and then building proper experimental procedures for those devices. And so in this case, we show that with just a single experimental setting, by attaching every noisy qubit to an ancilla qubit, you can extract all the information about the device noise in one shot. And then here we're showing how you can extract information more efficiently from quantum systems using things like shallow shadows. And that's another intersection that we're looking towards in the future, is combining this MPL work with this efficient shallow shadows work and combine the two to get more information to the device faster. And so just one more step, like thinking of the far future, some of these more corporate slides that I have here, is that all the experiments you're looking at today, they have to do with error mitigation, and they have these overheads, as some of the audience alluded to, this exponential overhead. They might not necessarily scale well in the far future. And so the actual focus of much of the research at IBM Quantum now is not necessarily experiments like these anymore, although they've been very helpful and we want to continue doing them. We want to think about quantum computing now towards the long term using error-corrected qubits. And towards that end, there's been recent work published in Nature by his colleagues at IBM on developing these highly efficient error-correcting codes. And this is going to be in service of this future device with over 100,000 qubits, hundreds or thousands of just logical qubits. And we're going to have to augment the devices with long-range connectivity, higher connectivity to get to this point. And so the mission now is actually stretching out to many, many years, all the way up to 2033, where I might sit at, let's say, like this layer or so, but then there's folks developing devices with more and more qubits, more and more connectivity, different kinds of long-range connectivity. There's a lot of work going into the software as well to access these devices on a reliable way, and going all the way up to the algorithms that anybody can try to access. So this is the work that I'll be working on, the rest of the team will be working on beyond what I'm showing today. So with that, I'd like to thank you for your time and your attention. I'm happy to take any questions.
So time for questions, comments. Yes. Thank you. This was very impressive. And first, I have a comment about the first claim part. So you had a reference to Shiraishi Matsumoto, but this same Naoto Shiraishi some years ago proved that many spin chains in one dimension with spin 1/2, they do not possess local conserved quantities as defined in this case. So it's a very nice work. And also, if you're interested in, there is a poster by his student, Yamaguchi, in this Mizuki in this talk, in this session. So as a conference, so please go there. And okay, so here's a trivial, nasty question now. So you jumped into MBL, but isn't it possible? Why don't you first do something like so? The case where you know exactly what conserved quantities are. Like I don't know if you have XY model counterpart in fluid dynamics, but I mean, isn't it possible to do something where you know the answer and confirm that?
Yeah,
your thing?
like a proper control experiment on the device. Actually, one could do the the ZZ icing chain that I said in the very beginning of the toy example. Yeah.
And does it work?
We didn't do it. That's a good point. I think that
No,
it's a fair question. I think the reason we don't is we were trying to push on like various directions, and so I probably gave a very heavy perspective here. Oles was particularly interested in like finding UFO case systems that exhibit this kind of behavior and then just playing with them numerically and showing them. So I think like chronologically that's how it happened, but I think it's a very good point and something we could look at. The difference though is that doing a simple system like that, it would just be so much easier because you're measuring out in so many fewer bases, and then many of the problems that we encountered and the solutions we developed would never have had to happen in the first place, right? Like these different ways of like extracting local information very efficiently across the device and post-processing it efficiently. You wouldn't need to do that.
Thank you.
Yeah, I'm tempted to comment that we had a paper a couple of years ago doing the x-axis feature on IBM, I think. Yeah, but at least in our experiment, it decays very quickly. Actually. There's a room for improvement. We are not experts on all the computation and all that. But at least something. Yes, please.
One question. So when you were saying fluke, I mean, are you necessarily in the high drive frequency regime where the prethermal timescale is large and you can see these things, or have you studied what happens when you go to slightly lower frequencies where things are supposed to heat up, and given a strength of disorder, there is a competition as to how fast this can happen? I mean, this kind of stuff. Have you?
So would that manifest in the circuit? Would that be like a smaller theta or something? Larger theta?
I think this concept of this local integrals of motion. I mean, well, I'm not an expert in this MBL stuff, but this is supposed to go away if the heating is large and you go to this infinite temperature fixed point and stuff like that. So you see decay of that. And how far? I mean, of course, I understand, but here you can only do 20 cycles. But if you're at sufficiently low frequency and reasonable disorder, even that 20 cycles might be enough to really heat up the system. I mean, at least from standard fluke. I mean, just wondering if anything like that can be seen here.
Yeah, I would have to know how that converts into like the circuit language, I guess, like what sets of parameters. But my guess is that it would be straightforward because it's a fully controllable device, right? So any combination of disorders and data you want to do, you can do with that basically no change to how it's executed. And then in terms of whether we actually did it, I'm sure I have to know what the mapping is. Yeah, but I'm not in time with that.
Yeah, sure.
Question. So you know explicit the expression for the local integrals motion, right? So at least for maybe 20 qubits, 50 qubits, etc. But then can you try to extract some physics or some general pattern out of it, like a decay pattern and size, or because it could be something out of it, right? So you don't have so there seems to be a avenue for extracting something out of it, and I wonder, but I have no idea what exactly that is.
I think that was our issue as well. Is like we went through all this effort of getting Leons, and at some point we were like, what do we do with these? I think this is the maybe close to what you're describing, is we're looking at the localization lengths and also the dependence on the weight of the poly, kind of something like this. And then this lot here, more of that. I don't know where I am now. Oh, this one here, these site-based localization lengths, I think also exactly what you were saying. But I wouldn't say this is anything too deep, physically speaking. This is more of a summary of what's going on. I think to show something deeper physically would be an experiment where we maybe propagate forward on the device, measure something out, and then try to propagate backwards using knowledge of the leons. I think that could be quite interesting. We just never got to that.
I see.
Yes, questions. Yes. So I'm very curious on the fate of the MPL transition in 1D, both in 1D and 2D. You mentioned in the future perspective. So now at this stage, I believe that it is not still reached to asking concrete question to that. But do you have anything to for answering?
You mean just you're asking about the theoretical fate?
No. Yeah. It is, I'll say, there is large debate among the fate of the MBA transition.
It's something about the tremendously large scale.
Yeah, I'm curious about that. At this stage, it is already reached to the, for example, like at least for 1D system, it's reached. Yeah, but I'm asking about. Yeah, I'm not asking to theorists.
I can't say I'm too updated on what the theorists and computationalists are doing, but my understanding is in 1D, it's like tens of thousands of qubits for long times, and so you have errors order probably like very small, right? Here we get errors of 1e minus 2 if we're lucky. So I don't think we're anything in that kind of regime. But what we can say is that at least we can observe this like finite size phase transition through this 1D, one-dimensional, 1PDM stencil matrices. And so from like 6 to 10 qubits, we can see this transition.
According to David Hughes, it's a sort of crossover, not the MBO transition, but it's still interesting.
Yeah. We can go to the same regime.
Then you can complete outside of being an experimental particle physics and all of it. We struggle early days of transistor circuit because of the noise. My simple question is that you had a qubit display and there are two very noisy, or you call it ergodic.
Yeah.
Is it possible to weed out some of them and improve the noise quality, or have we done that kind of thing?
No, absolutely. I think that the onset of these noisy qubits is often not quite understood, or if they are understood, it happens very stochastically. And I think Google has a lot of these experiments actually investigating these things called two-level systems and how they're formed. But it is quite straightforward to weed them out. You just run these jobs in between your experiment jobs that just quickly probe the system. So you might quickly check the decoherence time of every qubit. And if they're bad, you just don't use it, or you just wait a little bit, or you tune the frequencies of the qubits around so you avoid these kinds of systems. These tools are becoming more and more available. I would say at the time that we did this experiment, which is at this point 1.5 years ago, we had none of these tools, kind of like homemade ones. Nowadays, though, these kinds of checks are being done regularly, and the devices are a lot more stable as a result. Yeah.
Okay, any other questions, comments? If not, let's direct again.